Okay, this is my recording for Unit 1 exam part 1. Okay, define homeostasis. Homeostasis is the body's ability to maintain a balanced condition or internal state. An example of this would be that the body tries to maintain its body temperature when it is cold outside or hot outside of its body. To do this, there must be a receptor that senses the outside temperature, which communicates to the control center of the body. This is considered the afferent pathway. And then the control center also communicates to the effector, which then changes or helps bring the variable back to its homeostasis or set point. That is considered the efferent pathway. Negative feedback loops are the natural response that brings this variable back to its set point. A positive feedback loop would be something that derives that variable away from its set point, even farther away. An example of negative feedback would be, like I mentioned, the body senses that it's either too hot or too cold outside, and let's say it's too cold outside, the body would then shiver, causing the body to heat up against that cold exterior environment. An example of a positive feedback loop would be when an example of childbearing, and that Pitocin causes the contractions to increase. Let's see. So there are different types of mediated transport in the body. First one you have is a simple diffusion, which is the natural direction of solutes moving down the gradient from a high to low gradient. And this happens just naturally. It permeates through the membrane of the cells and into the cells if that's the lower gradient. Then you have facilitated diffusion, which still is considered molecules moving down their gradient, but this time it is with things that are too big or lipophilic molecules who can't permeate through the membrane. So they use these proteins to create channels into the cell or out of the cell, whichever direction it may be. The three types of those protein-mediated transports are mechanical channels proteins, which are opens through either pressure or some sort of movement. Another one is a electro based channel that opens depending on the charges of molecules, whether inside or outside the cell. And the last one is a ligand-gated channel, which could be any sort of molecule that binds to the protein that then open the channel. Then you have the primary and secondary active transport systems. These require ATP, which uses different mechanics to allow for transport. Primary active transport is when ATP is engaged directly with the protein and then allows certain selected molecules to enter through the system. And I would further explain what selective means later on. And the secondary protein, active proteins, are channels that indirectly uses ATP. So from the system of primary active transport, there is a gradient of molecules going against itself, against the gradient, because of ATP allows this. As that molecule is being moved against this gradient, it will help another set of molecules through secondary transport to follow that other molecule going against this gradient. Same thing there. little detail to add is that there is a relation of symports and antiports when it comes to that. So symports are when both molecules move together in the same direction, and an antiport is where they'll go opposite to each other. Yes, so let's see. So specificity is a concept that even though these channels open, it is not a random selection of which molecules are allowed to go in and out. It's actually still specific to what molecules that the cell may be looking for to either take it in or release it out of its cell. So the rate at which these molecules move depends mainly to their gradients and how saturated it could be. Or so, for example, if the cell or the molecule is greater on the inside of the cell compared to the outside of the cell, right? There's more solutes there. It is wanting to be balanced out more by coming releasing out of the cell because there's more space there for it. The greater that difference, the more higher that rate of diffusion can be. But it can also be limited to the amount of channels or the ability of it to be exiting out of the cell. So in a sense, since those limited channels are available to the cell, there can be competition of which molecules can use those channels to go in and out of the cell. And also, not only is there competition between different molecules, different types of molecules, there's also a competition of saturation in the sense that, let's say there's only a limited number of channels, only so many molecules can go through that at the highest rate possible before it becomes too crowded enough to even increase that rate. That molecules will have to kind of slow down or maybe even taper off at a equal level of its rate. And then direction of it, like I said, just depends on which direction the gradient is, or depending on whether ATP is involved to make it go against its own gradient. That direction is solely based on just osmolarity. Okay, and then speaking of osmolarity, what is it? So what is osmosis is the question you might ask. Osmosis is the movement of water between the semi-permeable surface or membrane, right? For osmolarity, the difference between that and molarity is that those molecules are actually placed in water, which creates a different scenario when it interacts with its environment, which we can talk about tonicity. So because of tonicity, osmolarities can be different compared to molarity, where tonicity is how osmolarity interacts with different environments, such as the cell compared to its bloodstream. So for example, we may have a isoosmotic solution, but can be a hypotonic solution to its cells. What does that mean? So iso meaning same, and osmotic. Isoosmotic means that the concentration per liter of the outside of the cell, so the solution, is the same as what's inside the solution. And then hypotonic means that basically means that there is less solution dissolved in the solution outside of the cell compared to the inside of the cell, which means there's a higher concentration inside the cell, and thus meaning that water will try to move towards wherever there's more solutes or higher concentration. And so for this scenario, if a solution is hypotonic, the water would try to go into the cell away from the outside of the cell, since it has a higher concentration. Yes. So we have thus described most of everything in this part 1 section, including homeostasis, how this works with both afferent and efferent pathways, with both negative and positive feedback loops. There's still more different kinds of feedback loops. We'll also go into detail with that. That is that with negative feedback loop, its goal is to try to bring the variable back to its set point or towards homeostasis. And if it is unable to do so, right, that effector is trying to get there, but it is unable to resolve that variable, it is considered inadequate. So it's an inadequate negative feedback loop. And so there's also another one, which is considered the forward feeding feedback loop, sorry. And this is where multiple effectors will cause each other to stack and to help create that variable to get back to its homeostasis. So for example of that is if, let's say, you see food, that causes an effector to create saliva in your mouth, and in which when the saliva in your mouth is being released, then your gastric systems, the stomach acid, in your body is starting to secrete as well, which will help digest the food you eat that you are seeing. So all that just kind of binds from each other. If one thing happens, then the next will also start, and and so on. Let's see. I believe that is everything. So thank you for listening to this part 1 of the Unit 1 exam.